Good morning to all of you. I welcomes to all in our lecture series on statistical mechanics, that is your core paper 14, belongs to 6th semester BSc syllabus. In our last class we have been discussed Gibbs paradox. With the help of two videos we have been completed this topic. I suggest to all of you that before you have to watch this today's video, at least you go through this Gibbs paradox video. Okay, second part, at least you have to go, and you can found that the Gibbs paradox has been given the correct entropy, which will be called as the universal entropy, can be used in distinguished particles or molecules and indistinguished particles and molecules. So this is your uh, corrected entropy given by Gibbs, that is your nk ln v by n into h by q 2 pi mkt to the power 3 by 2 plus 5 by 2 nk, and this expression is also called as your Sacker tetrad equation. Okay, this is Sacker, SACKUR Sacker tetrad formula or equation. In our today discussion, we have to we are going to discuss about entropy of a perfect gas using the classical microcanonical ensemble. So at the end also we are going to be found the same entropy whatever we found in the in our Gibbs paradox, that is a Sacker tetrad equation, also we are going to be found at the end of this topic. So let's start. Okay, let us consider a micro canonical ensemble of a perfect gas having n numbers of point particles, each of mass m in a volume v, enclosed in a volume v, with total energy E. The number of whole phase space is tau. Okay, now consider a hypervolume which lie in between E and E plus dE each. Let this is del tau will be equal to integration of dq1 dq2 up to dqn, because these are the generalized coordinate, and we know that if we have a point particle, then that point particle has three position coordinates and three momentum coordinates. If only one particle, if we are going to consider if one particle, then it has, if point particle, one point particle, then it has three position coordinate, three momentum coordinates, so total six coordinate we can found. Likewise, if we are going to consider n point particles, so it will be 3n position coordinates, 3n momentum coordinates we can found. In detail we have been discussed in our last videos. I'm going to show you. Wait, you can check this topic. Okay, whenever we have been discussed dimension of phase space, at that time we have been discussed if a single particle will be in a 3D space, then it has 6 degree of freedom, means three position coordinates, generalized position coordinates and three momentum coordinates. And if n number of particle, or we are going to consider 5 particles, then it will be 5 into 6 equal to 30. That means here total coordinates or degree of freedom we found 6. So for 5 particles it will be 5 into 6 equal to 30, or we can write in this way that number of particles are 5 into position coordinates are 3 equal to 15. 5 number of particle, 3 momentum coordinates 15, 30. In this also it can be represented. So I suggest to clarify over these dimensions and degree of freedom, etc., you can go through this video. Okay, wherever we have been discussed dimension of phase space. So here, if we are going to consider a small or hypervolume in the phase space tau, and the hypervolume is in the energy range E and E plus dE, then the volume d tau will be integration of dq1 into dq2 in up to dq3n into integration of dp1 into dp2 into up to dp3n. Let it is your equation number 1. Okay. Regarding hypervolume also we have been discussed in this topic, density of distribution in the phase space. You can check in that video. Here also we have been discussed d tau, dq1, dq2 up to dqf. Here it is in generalized way. Okay, here we don't know the particle will be a monoatomic or diatomic, that we don't know. So generalized, in the generalized way we have been written f. The here capital F represents your degree of freedom of the system. Okay, this of the ensemble, and here d into dp1 dp2 up to dpf, that will be give you the volume of infinitesimal region or d tau in the phase space. So here hypervolume, whatever we have been considered, the volume will be in the range E and E plus D, and the volume will be this one. Let it is your equation number 1. Now the numbers of quantum states or the so-called microstates in the energy range E and E plus dE will be how much? Del tau by h to the power 3n. Why this is so? This is represents the hypervolume, right? And we discussed several times that suppose we are going to consider a point in the phase space. This is your phase space. A point represents a phase point, right? Phase point. If we are going to consider this point has not exact location. This point in the phase space, or we can say phase point, not have the exact location in the phase space, but it is constrained, or it has the dimension in a small volume. Okay, according to Heisenberg uncertainty principle. How it is, why it is, you can go through that video. That if we are going to consider a single phase point, then according to Heisenberg uncertainty principle, this point is enclosed by a small volume that will be HQ. Okay, because for a single phase point, the coordinate or the location in the phase space will be dx, dy, dz, dpx, dpy, dpz. Okay, so dx into dpx, if we are going to consider dx, dpx approximately h according to Heisenberg uncertainty principle. Likewise dy, dpy also h, dj, dpz also h. So here this location is not exactly can be defined in the phase space, but it has to be uncertain in a small volume. With the help of Heisenberg uncertainty principle, that elementary volume have the size h into h into h, HQ. If HQ will be for single particle, then for n number of particle it will be h to the power 3n. Okay, so here h to the power 3n is the volume of uncertainty if we are going to consider n number of phase points in the phase space. So this is not the point. This is actually a small volume having the dimension h to the power 3n. So here phase point means this point will be not located exactly at a point, it will be in the uncertainty form along x and px. That means it is considered as variation of its xpx in a small volume according to Heisenberg uncertainty principle. So hence the number of quantum states. So as we discussed that each and every point in the phase space is called as the phase points. Also that is represent the microstates. So if each and every point has the volume or enclosed, we can say enclosed by a volume or represented by a elementary volume having the volume is h to the power 3n, and we consider a hypervolume in the range E and E plus delta E delta, the number of quantum states, number of microstates, or we can say that the number of phase points will be the hypervolume whole divided by the phase points. So this is nothing but the phase points. Okay, sorry, volume of each phase point. This is nothing but volume of each phase point. So this is the dimension in which each of phase point has been enclosed in the phase space. So again I am going to tell that in the phase space, if we are going to consider a phase point, the phase point could not be exactly located in the phase space, but however this will be in the uncertainty form according to Heisenberg principle in a elementary volume. If we are going to consider a single particle, that volume will be hq. If we are going to consider n number of particles, that elementary volume will be h to the power 3n. So if we are going to consider delta is a total volume, then in that delta, how many number of quantum states or phase points will be found? That will be delta by h to the power 3n, right? Now 1 by h to the power 3n, I have to put instead of delta this one. Okay, let this is your equation number 2. Here I written h to the power 3n is the volume of a elementary cell in the phase space. Okay, volume of the elementary cell in which I have to write here, it will give you clarification in your future. Whenever you are going to study your note, at that time it will give the clarification. Volume of elementary cell in the phase space in which in bracket you have to write in which phase point or microstate is enclosed by Heisenberg's uncertainty principle. You just write this one here. Okay. As the particles of a perfect gas are non-interacting, the energy of a perfect gas is independent of the position of the particles, right? We know that in case of perfect gas, the molecules or the particles are non-interacting. The energy, the energy of perfect gas is independent of the position of the particles. Hence, the energy of a perfect gas is independent of position of the particles. Now, therefore, dq1 into dq2 up to dqn will be give you v to the power n. V is the volume of the single particle. Actually, it is not called as the volume of the single particle. Here I have to just modify the language. Wait, here I just modified the language. This V is the volume in which single particle is in dynamics. Okay, this is your whole volume. If we have a single particle, then it has generalized coordinate is how much? What are the generalized coordinate? Dx, dy, dz, right? If I am going to integrate, then it will be see, this is the integration, not the single integration. Okay, here the integration of see, for one particle integration should be 3. Along x-axis we have to consider all the length, along y-axis consider total length, along z-axis also we are going to consider total length. Then if we are going to consider x, y, z axis, or along x, y, z total length, then if I am going to multiply, this will not called as the V, it will be called as the V. V means volume of the enclosure, volume of the vessel we can say, or we can say the volume in which single particle is in dynamics, right? For the single particle, it has to be integration has to be 3 times. For n number of particle, it has to be integration up to 3n times. So you don't think that this is the only single integration. No, this is the numbers of integration up to 3n. That means integrations, 3n integrations, you can say 3n numbers of integrations. This is represented by single integration, but this single integration is nothing but 3n numbers of integrations. As we here found, for a single particle it has 3 integrations, so hence for n number of particle it will be 3n integrations. Okay, so for single particle we found that it will be the volume will be V in which that particle is in dynamics. Okay, likewise if we are going to consider all the particles and their corresponding generalized coordinates, integration of generalized coordinates, obviously we are going to found V into V into V up to n times, that means V to the power n. Okay, you just remember what I explained. The same concept we are going to be used whenever we are going to discuss canonical ensemble. Okay, this expression it will be required, that integration over dq1 up to dqn will be V to the power n. Okay, hence equation number 2, this equation number 2 is going to be right, or the equation number 2 will be this one by h to the power 3n into V to the power n integration over dp1 up to dp3n. Here again I am going to tell to you that this is not a single integration. This represents 3n times integration. Okay, now here we have been considered that del tau by h to the power 3n is W. You just recall, the W represents the probability, thermodynamical probability of a macrostate. W is nothing but your thermodynamic probability, which is proportional to the also entropy. So why it is called as this term will be called as the entropy? See, this is what? This is the number of quantum states or microstates in a given energy range, or for a particular macrostate, right? Quantum states or microstates in a given energy range or a particular macrostate. W means what? W means also the same, the number of microstates. Okay, so if this is represents microstates, number of microstates, so here we can write W. So that implies W equal to this much. Let it is your equation number 3. The integral in equation number 3, that is this one, represents the volume occupied between 3n dimensional hypersphere of radius 2me to the power 1 by 2 and 3n dimensional hypersphere of radius 2m e plus d to the power 1 by t. Oh, sorry, 1 by 2. What is this? I am going to explain. You just watch. So first of all, you can see that this is in the dimension of momentum, but we have been choosed the range is the energy E and E plus D. You just recall that whenever we have been discussed uh, evaluation of number particle in momentum range P and P plus dp at the time of your Maxwell's Boltzmann distribution, just after Maxwell's Boltzmann distribution, we discussed evaluation of number of particles, number of molecules in momentum range P and D, P plus dp. At that time, this is the sphere. So in between this, the dots are represents momentums of the molecule. So here we discussed about a single molecule and its corresponding momentum, how much will be in between this sphere having the radius p plus dp and p. In between these two sphere, what are the probable momentums of a molecule? At that time we have been discussed. Okay, so here, as we have been considered the energy range E and E plus D, but integration is in the form of momentum, then we know that p square by 2m equal to E and p equal to 2me to the power 1 by 2. So here this momentum dimension can be changed to energy dimension, and we are going to consider the two hyperspheres having the radius p, that is nothing but your 2me to the power 1 by 2, another sphere that is your p plus dp, or nothing but your 2me plus de to the power 1 by 2, right? So so this is nothing but volume occupied in between these two sphere having the radius 2me plus d to the power 1 by 2 and another sphere radius 2me to the power 1 by 2. Okay, so same thing it has been written over here. So this integral represents the volume occupied in three-dimensional having the three-dimensional hypersphere of radius 2me to the power 1 by 2 and 3n dimensional hypersphere of radius 2me plus d to the power 1 by 2. Next we have to go for the next page. In general, volume of 3D sphere of radius r is nothing but 4 by 3 pi r cube. Here it is written as V of 3. R means representing the radius is r. This 3 represents 3-dimensional. Okay. Here 3 represents 3-dimensional. For 3-dimensional sphere, 4 by 3 pi r cube. This 4 by 3 pi r cube can be represent or can be written as pi to the power 3 by 2 divided by gamma 3 plus 2 by 2 into r cube. You just solve it, we can found this one. You can see that pi to the power 3 by 2 by gamma to the power 3 by 2 plus 2 3 plus 2 by 2 into RQ, right? Here I solved. See, uh, wait. 1 second, 1 second, 1 second, 1 second. So it can be written as pi to the power 3 by 2. This will be gamma 3 by 2 plus 1 RQ, right? So it will be pi to the power 3 by 2. Gamma 3 by 2 plus 1 is nothing but 3 by 2 gamma 3 by 2 into RQ. Then pi to the power 3 by 2, it can be written as 3 by 2 gamma 1 by 2 plus 1 into RQ. Pi to the power 3 by 2 by 3 by 2 into 1 by 2 into gamma 1 by 2 into RQ. Pi to the power 3 by 2 by 3 by 2 into 1 by 2 into gamma 1 by 2 is nothing but root pi into RQ. So if we are going to solve this one, see, pi to the power 3 by 2, if this root pi will be moved to the numerator, it will be pi to the power 1 by minus 1 by 2 RQ by, this will be 3 by 4. It will be 4 by 3. See, 3 by 2 minus 1 by 2 is nothing but pi. 4 by 3 pi RQ. So here, this 4 by 3 pi RQ can be represented by this. So it will be pi to the 3 by 2 by gamma 3 plus 2 by 2 into RQ, or it can be written as pi to the power 3 by 2 gamma 3 by 2 plus 1 cube, as I solved here also. Or it can be written as pi to the power 3 by 2 into 1 by 2 gamma 1 by 2 into RQ. That implies V3R can be written as gamma pi to the power 3 by 2 into R to the power 3. Here 3 by 2 factorial gamma half. Let it is your equation number 4. So now we are going to write in generalized form whenever we are going to consider 3n dimension. You can just focus here that here pi to the power dimension, 3 means dimension, RQ, this represents dimension, right? Here 3 represents dimension. So if dimension is going to be changed from 3 to 3n, then it will be 3n by 2 r to the power 3n. This will be 3n by 2 factorial. Like that we can write in general. Okay. So therefore for 3n dimensional hypersphere of radius 2me to the power 1 by 2, the volume will be how much? V, this will be 3n, this is in subscript, okay, 3n r 2me to the power 1 by 2 will be written as pi to the power, instead of 3 we have to write 3n by 2, here 3n by 2 factorial into 2me to the power, this is radius, 2me to the power 3n by 2. Now you are going to be think that where this gamma half has been gone. I am going to explain. Here you can see gamma half has been neglected for large number of particles. How it is I am going to explain. You just watch. Here I told that if we are going to consider large number of n, large number of gamma 1 by 2 has been neglected for large number of particles. See, for single particle it will be only 3 dimension, right? 3 dimension, that means we are going to be consider how much? It will be gamma here 3 by 2 plus 1, gamma 3 by 2 plus 1. We found that I'm telling about the denominator. You just concentrate at denominator, right? Okay, 3 by 2 plus 1 means this will be 3 by 2 into 1 by 2 into gamma 1 by 2. Gamma 1 by 2 value is nothing but root pi. Okay, so 3 by 2 into 1 by 2 into root pi. Okay, here I told that if number of particle is going to be large, then this gamma half, here I have to write gamma half equal to, gamma half equal to root pi has been neglected. So gamma half value root pi will be neglect. How? You just see here 3 dimension. Now you just consider 10 dimension. It will be 10 by 2 plus 1. Okay, see, two things will be arise. If this n this n will be even, then we are not going to found any root pi. Only for n equal to odd, we are going to be found this root pi, and it will be neglect automatically. See, now we are going to consider even 10. It will be how much? Gamma 5 plus 1. That means it will be 5 factorial. There is no root pi term has been came. Okay, leave it. Now you consider odd. Suppose gamma 11 by 2 plus 1. So what we are going to get? This here we can get that 11 by 2 minus 1, 9 by 2, 7 by 2, 5 by 2, 3 by 2, then 1 by 2 into gamma half. So here you just see in the denominator, when we consider n equal to odd equal to 11, here is the denominator. We found that this much into gamma half. Okay. At the meantime, the numerator will be how much? You see, the numerator should be pi to the power 3 by 2. That means pi to the power, wait, I have to write full expression for n equal to 11 degree. 11 if n equal to 11, then numerator will be how much? Pi to the power 11 by 2. Pi to the power 11 by 2. The denominator will be this much. That will be 11 by 2, 9 by 2, 7 by 2, and 5 by 2, 1 by 2, and gamma half is nothing but pi to the power 1 by 2. Right? Okay. Now you just see this pi by 2, when it will move to the numerator, it will be how much? Pi to the power 11 by 2 minus 1 by 2 will be how much? Pi to the power 10 by 2. That means you just think pi to the power, this is nothing but pi to the power how much? 5.5 minus pi to the power 0.5. This is for n equal to 11. If we are going to consider n is very large, suppose n we are going to consider, see, for the even, this root pi not at all come into the picture. Okay, that for the n equal to even, if we are consider, this root pi will be not come into the picture. But if n is very large means you can consider even, we can consider also odd. So for even case, this is not came. Okay, for odd case, it will be creating the confusion. No, you see, for the odd case, we are going to consider 999. Suppose we consider the 999 case, n equal to 999. So the numerator will be pi to the 999, and the denominator will be how much? This will be what? This will be gamma 999 by 2 plus 1. So if I will be expand, then at the end I am going to found pi to the power 1 by 2, one term. Right? Now you take this one to the numerator. So pi to the power 999 into pi to the power minus 1 by 2. And other terms, whatever we are going to get after expansion of this. Okay, this, if I am going to expansion, this will be how much? 999 by 2, then 997 by 2, then 995 by 2, like this. So here, whenever this pi to the power 1 by 2 gone to the numerator, you just see here pi to the power 999, here pi to the power, that means pi to the power, this will be 999 by 2, 999 by 2, okay, 999 by 2. So it will be this will 999 by 2. So because here see, for 3 dimension it will 3, for 999 dimension it will be how much? 999 by 2. So 999 by 2 means pi to the power 4 4 it will be 499.5 499.5 into pi to the power minus 0.5. So and the denominator will be not going to be affect anything. So here pi to the power 449.5 into pi to the power minus 0.5 means how much we are going to get? Pi to the power 449. So here whenever we are going to consider large number of n, you just see, is there any great change? Is there any significant change? The change is very minute. Now you are going to consider n will be equal to 1 7 5 6 8 9, this much large number. So the numerator will be pi to the power this much by 2 into pi to the power 0.5. So this will be how much? 8 7 pi to the power 2 into 2 divided by 17, 8, then 15, 2 7, then 8, then 4, then 8.5. So if we are going to consider this two term, then it will be pi to the power 87848. Is there any large change we are going to be found? No. So hence here for large value of n, the gamma 1 by 2, that is root pi, has been neglected. Okay, so here gamma 1 by 2 or root pi has been neglected for large number of particles. Okay, similarly for 3n dimensional hypersphere, here for 3n dimensional hypersphere, radius this one. Now we are consider radius 2m e plus de to the power 1 by 2, then the volume will be here 3n, radius is the function, this volume function of this radius to the power 1 by 2. We are going to get pi to the power 3n by 2 divided by 3n by 2 factorial, and this r to the power 3n, r to the power 3n, but the radius is 1 by 2, so 3n by 2. Okay, got it? This is your 5, this is your 6, but we have to find out the volume enclosed by these two sphere. We intend to find out the volume enclosed in between the two spheres. So which one is the larger sphere? This one is the smaller sphere, because the radius here is the larger, radius is smaller. So the enclosed volume in between these two hypersphere will be this minus this. Okay, therefore the volume occupied in between hyperspheres of radius this and this will be how much? Whatever we intend to find out, this one, this integration dp1 into dp2 up to dp3n will be equal to how much? It will be, you just see that this coefficient is same, can be taken outside, pi to the power 3n by 2 by 3n by 2 factorial into this radius is larger than this radius, so this minus this, so 2m e plus e de to the power 3n by 2 minus 2m e to the power 3n by 2. Okay, so now by subtracting these two, neglecting other terms, we are going to find out, this is as usual we have been written, and this will be 2m e to the power 3n by 2. So it will be equation number 7. Okay, so by subtracting the volume having the radius this one and this one, we found this one, pi to the power 3n by 2 by 3n by 2 factorial into 2m e to the power 3n by 2. That is your equation number 7, neglecting other terms. So how we got this? By subtracting this and this, Here I am explaining, you just watch. So this minus this will be equal to approximately this one. How it is? See. So here 2m to the power 3n by 2, 2m to the power 3n by 2 taken outside. So the first term will be 3n by 2 minus e to the power 3n by 2. Now you take e to the power 3n by 2 common from this 2, then it will be 2m to the power 3n by 2 into e to the power 3n by 2 into this will be e plus d to the power 3n by 2 divided by e to the power 3n by 2 minus 1, right? So equal to, this can be written as 2me to the power 3n by 2, right? So this can be written as e plus d by e whole to the power 3n by 2 minus 1, right? So 2me to the power 3n by 2 into, here this can be written as e by e, that means 1 plus d by e to the power 3n by 2 minus 1 is equal to 2me to the power 3n by 2. Here we are going to use the binomial expansion. In general, binomial expansion is nothing but a plus b to the power n is nothing but nc0 a to the power n b to the power n minus 1 n minus b to the power, here a to the power n minus 0 b to the power 0. Then second term will be nc1 a to the power n minus 1 b to the power 1, nc2 a to the power n minus 2 b to the power 2 up to ncn a to the power n minus n b to the power n. This is the binomial expansion. Here also we are going to use the same. Here n in this case n is nothing but 3n by 2. So here if I am going to expand with the help of binomial theorem, it will be 3n by 2 c0 1 to the power 3n by 2 into d by e to the power 0. Second term will be 3n by 2 c1 into 1 to the power 3n by 2 minus 1 into d by e to the power 1. Okay, the third term will be 3n by 2 c1 1 to the power 3n by 2 minus 2 d by e to the power 2 and so on. The next term will be d by e to the power 3, like that, and the last one is minus 1 minus 1. Okay, now see 2me to the power 3n by 2 into, here you can see 3n by 2 c0, that means it will be how much, 3n by 2 factorial divided by 0 factorial into 3n by 2 minus 0 factorial, and this value 1 to the power anything will be 1, something to the power 0 will be 1. The second term will be how much, you can see 3n by 2 minus 1 factorial divided by, sorry, it will be 3n by 2 factorial divided by 1 factorial into 3n by 2 minus 1 factorial into 1 to the power anything will be 1, this will be d by e. Okay, then third term will be this one. This one I am not writing because you can write here. I am concentrating over this term, plus dot 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 1. Okay, next space has been completed. Here I am going to do, see, only another 2 steps. See, it will be 2m e to the power 3n by 2. Okay, this will be how much? This first term will be 1, second term will be we can get only 3n by 2, because 3n by 2 factorial in the numerator, denominator 3n by 2 minus 1 factorial. So in the numerator, this 3n by 2 factorial can be written as how much? 3n by 2 into 3n by 2 minus 1 factorial. So this got cancelled, only we can found 3n by 2 into d by e. Second term will be you are going to get 3n by 2 into 3n by 2 minus 1. Then 3n by 2 minus 2 factorial will be going to cancel out. Next, del e by e square plus dot dot minus 1. Okay, so here you can see plus 1 minus 1 got cancelled. Here see, this is the first term cancelled with here. Second, third term you can see that we are going to get the d to the power 2. The next term 1 2 3, fourth term we can found d by e to the power cube. Here d is very small, then d is small, d square will be very small. Okay, again d by e is there and square will be very small. That means other higher terms has been neglected. d by e square, d by q, it has been neglected. But it can be found that 3n by 2, so here one term has been left. So here 3n by 2 into del e by e, you can found here 3n by 2 is a number, right? Here del e by e also a number, because here the unit, there is no unit. Here is the energy, denominator also energy, so it is also act as a number. So 3n by 2 is equivalent to e by de. Okay, is equivalent to e by de. So or 3n by 2 into 1 by e by d will be equal approximately 1. Yes or no? 3n by 2 is a number and e by d also a number which will be equivalent, both are equivalent. So that means ax is equivalent to y. So ax into 1 by y will be equal to 1. Yes or no? So here this is equivalent to e by d. So 3n by 2 into 1 by e by d equal to 1. Yes or no? Now 3n by 2 into, I can write this 1 by e by d can be written as del e by e equal to 1. So here we have a term 3n by 2 into d by e. This will be equivalent to 1. So finally we got this one. Okay, so here here this minus this will be equal to this by neglecting other terms. So what are the terms has been neglected here, I explained. You can write in your rough. Okay, then so by doing this we found this equal to this, which is your equation number 7. Now substitute this value in your equation number 3. We are going to be found w equal to v to the power n by h to the power 3n into pi to the 3n by 2 by 3n by 2 factorial into 2m e to the power 3n by 2. Let it is your equation number 8. Now go for the next page. That according to statistical entropy, the statistical entropy sigma is equal to number of quantum states. Just before, what we found w in your equation number 8 is nothing but number of microstates. So here if statistical entropy is represented by sigma, then sigma will be equal to w. Okay, and here one thing you have to remember, that sigma is your statistical entropy, but if we are going to consider thermodynamical entropy S, then they are going to be relate with each other like this. Thermodynamical entropy will be equal to Boltzmann constant into statistical entropy. This proof is not in your syllabus. You just remember, it will be required in our forthcoming classes. Thermodynamical entropy is equal to Boltzmann constant into your statistical entropy. Okay, or you can just recall that whenever we have been discussed microstate macrostate, at that time also we have been found S equal to K ln W. Here ln W is purely your sigma, statistical entropy. So statistical entropy is nothing but your W, that means number of microstates. And as we discussed many times, that whenever W will be large, for that case it will be convenient that we have to be represent with natural logarithmic, that is log base E W, when W is large number, so it is convenient to represent by log. So sigma will be equal to log E W. See, this can be written as ln also, ln W. Okay, you can write ln W also, no problem. So log E W value, here I just substituted from equation number 8. Okay, from equation number 8 you just write, from equation number 8 I just substituted the value. Now sigma will equal to, you can see that this numerator term is nothing has been changed here, and denominator I kept s to the power 3n, and this term I taken this side like this, minus log e 3n by 2 factorial. Let it is your equation number 2. Now we have to consider Stirling approximation, that we know log e n factorial. Again I am going to suggest you, if you are going to be comfortable, that you have to write ln n factorial is equal to n ln n minus n, you can write, no problem. Okay, so here like this can be written as ln this much minus ln this much factorial. Okay, so in my note whatever I written log e this one. So here, from here onwards, whenever I am going to be explain, at that time I will be pronounce ln. Okay, instead of log e it will be so large, two words or so, somewhat long words to be pronounced. So instead of log base e I will be pronounce ln. Okay, and also I suggest in your note you can write ln n factorial like this. Instead of log e you can write ln. Okay, so here ln n factorial is equal to n ln n minus n. For large n we know that Stirling approximation, hence ln 3n by 2 factorial will be equal to 3n by 2 ln 3n by 2 minus 3n by 2. See, here it is written log e, but I am pronouncing ln. Okay, so no, not to be confused. Okay, now we have to substitute this value in the equation number 9 here. Simply I substituted. See, this is this minus this, here is the minus is there, so it will be minus 3n by 2 ln 3n by 2 plus 3n by 2. Okay, so it will be ln whatever written over here, nothing changed, you check it. Okay, in bracket same thing I have written, minus here 3n by 2 will be the power of the here, as it is ln 3n by 2, so this 3n by 2 will be power of this one, so ln 3n by 2 to the power 3n by 2 plus 3n by 2. Okay, now here you can see ln this much minus ln this much collectively can be written as ln, this is the numerator terms, here it is written. Okay, divided by this one 3n by 2 to the power 3n by 2. plus 3n by 2. Okay, carefully you have to write. Okay, carefully you have to write. Sometimes what is happening, you will be you are writing misconsciously, you will be leave this one, 3 will be leave or n will be leave. Okay, so consciously carefully you have to write. Sigma equal to ln. Here you can see each term have power n, v to the power n, h to the power 3n, pi to the power 3n, n. So this n can be power over here. Okay, so ln v by h cube into pi to the power 3 by 2 by 3n by 2 to the power 3 by 2 into 2m e to the power 3 by 2 to the power n plus 3n by 2. So sigma equal to this n can be taken over here, n ln v by h cube, this whole terms, pi to the 3 by 2, 3n by 2 to the 3 by 2, 2m e to the power 3 by 2 plus 3n by 2. Okay, now with this much and this much is equal, only I just written arrangely. Okay, just see n ln, here v is here, here you can see that 3n to the power 3 by 2, each of the power is 3 by 2, right? So here 2 is here, it can be moved to numerator, it will be 4. So 4 pi m by 3 to the power 3 by 2. Okay, here n is here, e by n to the power 3 by 2, hq plus, just I arranged these all the terms in this fashion. Okay, so it is your equation number 10. Now here it is required to recall the Gibbs paradox, whatever we have been studied in our last class. This is entropy we found. If we are going to use this entropy, this will be not always true, or this entropy expression could not be give the additive nature of the system. This will be only valid for the particles or molecules when distinguishable. That means A, B, C. If like this the particles are distinguishable, then this entropy will be useful, but this entropy could not be useful whenever the particles are going to be indistinguishable. That things we have been discussed in our Gibbs paradox. I'm just wait, I'm showing to you. Wait, see, at the time of discussing the Gibbs paradox, we have been used this one. Entropy is equal to this much plus 3 by 2 nk. Here you can see, yes, I told that S is nothing but sigma k. So if I am going to multiply k with this one, so it will be nk, this will be 3 nk by 2, and we are going to find s will be here nk, here 3 nk by 2. See, 3 nk by 2, here nk ln this term also equal to this one. How it is, I am going to show you. See, v by hq is there, 2 pi mkt to the power 3 by 2 is there, right? So if we are going to consider E equal to our 3 by 2 n 3 by 2, if we are going to consider E equal to 3 by 2 nkt, then what will happen? See, this 3 got cancelled, 2 1 2 will be got cancelled, it will be 2 pi m, 2 pi m n and n got cancelled, 2 pi mkt to the power 3 by 2. Okay, 2 pi mkt to the power 3 by 2. Also we are going to discuss in this topic, whenever we are going to be use E value, it will be modified to this one. Okay, so in the Gibbs paradox, we have been also consider the same expression, this one, same expression what we have been here we have by considering microcanonical ensemble. So here in the Gibbs paradox, we found that this expression is not holds good for the additive nature of the entropy whenever we have been considered indistinguishable particle. So what we done? We have been divided a factor, that is your n factorial, because you just go through that video. I have been detailed discussed in that video. To finding the correct entropy, we have been divided, or therefore we have to divide n factorial with partition function of the gas, because n factorial times it has been it has been counted whenever we consider indistinguishable particle. You go through that video detail, you are going to be found why we have to divide n factorial. Okay, so here also same thing we have to consider, that this entropy could not be used always for additive property. So we know that the entropy is always follows the additive property, but the expression equation number 10 does not satisfy additive property. You just in bracket you have to write. Also we concluded in Gibbs paradox. So in bracket you just write these things, but no need to write in exam. In exam, this is a separate topic, that is a separate topic. So you just write here I added 2-3 words, see, but the expression equation number 10 does not satisfy the additive property. Also which is concluded we have to write for which has been concluded in Gibbs paradox topic. For your understanding purposes I have been written. Okay, no need to write in your exam. And also I suggest that here I written so many things to correct this entropy. This much things also not required to write in your exam. Okay, you just write the gist of this writing, whatever you understood, just write to within 2 and 3 lines. Okay, which has been concluded in Gibbs paradox, because in this equation 10 volume B appears in argument of logarithmic. Therefore it is not possible to divide the system into two parts and to write the total entropy as the sum of sigma equal to sigma 1 plus sigma 2. So this mistake happens because for n identical particles, only identical, it will not give the correct physical information. N identical indistinguishable particles we must not count as different conditions, okay, or quantum states. For the total system, when we interchange the identical particles, see, I'm going to, this is two particles A and B, two states. How many ways they can be arranged? Suppose three particles, three states. How many ways they can be arranged? Obviously 3 factorial ways, right? That means you can say 3 factorial means 6 ways they can be arranged. Here I am going to show you. See, three particles, 3 states. How many ways? A B C, A C B, B A C, B C A, C A B, C D A. how many ways? 1, 2, 3, 4, 5, 6, 6 ways. That means 3 factorial ways. Also you can check that if you have 4 particles a b c d and 4 states, then these 4 particles, this is simple permutation. 4 factorial ways they are going to be arranged. But if these particles are indistinguishable, means it could not be distinguishable. That means it is fully identical. That's so that this particle gone to this state or this state, there is no effect. Okay, that means only one state is only one way it will be possible here, like this. So which one is the A, which one is the B, not to be distinguishable. So this 3 factorial is not going to be count. Hence 3 factorial has to be divided with the count. That means we counted this one, this one here. I'm going to show you. This one is your, well, this W is the total number of microstates, right? But in this W, if we are going to consider indistinguishable particle, the n factorial ways has been counted, right? But if identical particle or indistinguishable particle, means this is for distinguishable, whatever we derived with distinguishable particle. If we are going to go indistinguishable particle, means this n factorial is not going to be counted. So we have to divide n factorial, right? N factorial with this W. Otherwise, we are going to get whatever the entropy we are going to get, that entropy could not be universally acceptable. Only it will be accept for the distinguishable particle, not for the indistinguishable particle, right? So only for that, here it is written the same thing, same concept we have been discussed whenever we in your Gibbs paradox topic. There also you can found these things, why factorial n has to be divided. So total system, when we interchange identical particles in the phase space, this mistake leads to overestimate the volume of the phase space by a factor n factorial under classical condition. By taking this factor into account, the entropy will be W by n factorial. As W is large, so it is convenient that we have to represent by ln. So ln W by n factorial. Again, I am going to tell to you that here it is written log base E W by n. You can write ln W by n, no problem. Here also I am pronouncing ln for my easy explanation. So you can write ln W by n, no problem. So now sigma we found n ln v by n into 4 pi m by 3 to the power 3 by 2 into e by n to the power 3 by 2 by hq plus 5 n by 2. Let this is your equation number 2. Okay, sorry, 12. This is your equation number 12. Now we have to go for the next page. See, here I have been written directly. See, after dividing n factorial, this has been changed. If we are going to compare this equation number 10 and equation number 12, here only changed. This happens 5n by 2, and v is converted to v by n. You can see v by n. Only these two things has been changed. N is there. Here v changed to v by n, and here 4 pi m by 3 to the power 3 by 2 e by n to the power 3 by 2. This is also same. H to the power q, hq is there. This is 3n by 2, but this is 5n by 2. Only two things has been changed. 5n by 2 v by n. Here v 3n by 2. After correction, this has been, we found this one. This is also called as your square tetraloid equation. Okay. Now, how this happens? Each and every step explanations I have been done here. I written explanation of equation number 12 not required for your exam, but I suggest that you have to write in your note. Okay, may you are not going to write in your exam, but you write in your note like this, not required for your exam. Here I am explaining how from this we are going to get this. Okay, so this is your explanation. I am explaining very easy, you just watch. Sigma equal to log ln w by n factorial. W value is this much, only n factorial has been divided, so w value here you can see this one. Okay, v to the power n, h to the power 3n, pi to the 3n by 2 by 3n by 2 factorial, 2m e to the power 3n by 2. Just I have been substituted, only extra term is n factorial. So according to Stirling equation, we have to use this one, ln n factorial equal to n ln n minus n. Okay, and similarly ln 3n by 2 factorial will be 3n by 2 ln 3n by 2 minus 3n by 2. Now first we have to rewrite this expression as this one. So it will be here n factorial and 3n by 2 factorial can be written like this, minus ln n factorial minus ln 3n by 2 factorial, and other terms are v to the power n, v to the power n, h to the power 3n, pi to the 3n by 2, 2m e to the power 3n by 2. Okay, now sigma equal to ln, nothing has been changed in this bracket, minus here Stirling equation we have been used, this will be this one n ln n minus n, so here it is minus, so it will be plus n ln n plus this one, and we are going to be consider this factorial ln 3n by 2 factorial is nothing but your 3n by 2 ln 3n by 2 minus 3n by 2, so it will be minus, here is the minus, so it will be plus 3n by 2 ln 3n by 2. Very easy. Now here ln in bracket terms nothing I have been changed. Here you can see n is here, can be written as ln n to the power n, okay, plus n. Here 3n by 2 ln 3n by 2 can be written ln 3n by 2 to the power 3n by 2, right? This is 3n by 2. Okay, next here you can see that ln n to the power n minus ln 3n by 2 to the power n, these two ln minus ln, here minus ln, these two things can be written this way, 1 by ln in collectively can be written as ln this whole, okay, this much, into 1 by n to the power n into 1 by 3n by 2 to the power n, 3n by 2 to the power 3n by 2, right? Another two terms are n and 3n by 2 plus n plus 3n by 2. Okay, now n plus 3n by 2 is nothing but your 5n by 2. Here we can see n v to the n, in each term power is n is there. Okay, v to the power n is there, v to the power 3n means v to the power n is there, sorry, h to the power 3n means h to the power n is there, pi to the power n also there. So I can write collectively this power n can be written over here. See, if I am going to write by considering commonly the power n over here, it will be v, it will be hq, pi to the power n gone to here, okay, it will only pi to the power 3 by 2, 2me to the power 3n by 2, n has been moved to here, whole power means it will be 2me to the power 3 by 2 into 1 by n to the power n, n is gone to here, it will be only n into 1 by 3n to the power 2 to the power 3 by 2 whole to the power n plus this plus this is 5n by 2. So this n can be taken to the initial n ln, this will be v by n into 4 pi m by 3 to the power 3 by 2. See, this 2 multiplied 4 pi, see, this term have same power 3 by 2. So here this 2 term and this is another 2 collectively can be written as 2 into 2 4 pi m by 3 whole to the power 3 by 2. This is e to the power 3 by 2. Here n to the power 3 by 2. E by n to the power 3 by 2. Okay, this n is gone already already to here, b by n, and hq is here. Okay, plus 5n by 2. So this is the thing how it will be. Ln w by n factorial will be this one. Here I have been explained. You just write in your note. You may not, you are going to be write in your exam, but you should write in your note. This is also called square tetrad equation, or the corrected version of the entropy, which will be universal, is going to be accepted, distinguishable and indistinguishable particles. Now here we have to stop our today's lecture. Okay, in the next lecture we are going to discuss thermodynamical functions of an ideal gas by using your your entropy. Okay, next class we are going to discuss entropy will be this one, and internal energy, then relation between temperature and pressure, chemical potential of a perfect gas, these thermodynamic functions, or it is called as thermodynamic quantities, that we are going to discuss in our next class. So in short, I am going to tell to you that this sigma is nothing but your statistical entropy, and thermodynamic entropy is nothing but K into sigma. We found here entropy. By using this entropy, we are going to find out internal energy. You can see del E by del S is nothing but T. So from here, we are going to, by solving this one, we can found the internal energy. Then we have to find out, see, del S by del V, P by T. So from this, by using this S, we are going to found the expression which will be relation between P and T, and chemical potential also will be mu by T is nothing but del S by del N. And what will be the expression, that we are going to discuss in our next class. Okay, so thank you so much for watching this video. Thank you.